How did everything begin? The story of the universe starts approximately 13.8 billion years ago with the Big Bang, a colossal explosion that set everything into motion. Imagine a singularity, a point of infinite density and temperature, where all the matter and energy of the universe were concentrated. In an instant, this singularity expanded, marking the beginning of time and space as we know it. This event, the Big Bang, created an extremely hot and dense state, a seething sea of particles and radiation. As the universe expanded rapidly, it began to cool, allowing particles to form. In the first few microseconds after the Big Bang, the universe was a hot soup of fundamental particles, quarks, gluons, electrons, and photons. These particles moved at incredible speeds, constantly interacting and colliding. The temperature was so high that quarks and gluons couldn't combine to form protons and neutrons. Instead, they existed in a plasma state, a sort of subatomic soup. As the universe continued to expand and cool, quarks combined to form protons and neutrons. This process, known as baryogenesis, was crucial for the development of matter as we know it. Within the first 3 minutes, these protons and neutrons started to combine through nuclear fusion to form the nuclei of the first atoms, primarily hydrogen and helium, in a process called nucleosynthesis. The conditions were just right for this primordial nucleosynthesis to occur. If the universe had expanded too quickly, it would have cooled too rapidly for fusion to happen. If it had expanded too slowly, it would have remained too hot for atoms to form. The balance achieved was perfect for the creation of the lightest elements. Around 380,000 years after the Big Bang, the universe had cooled enough for electrons to combine with these nuclei, forming neutral atoms. This era is known as recombination. The formation of neutral atoms allowed photons to travel freely for the first time, making the universe transparent to radiation. This moment is captured in the cosmic microwave background (CMB) radiation, the afterglow of the Big Bang that we can still observe today. The CMB is a crucial piece of evidence for the Big Bang theory. It provides a snapshot of the universe at a time when it was just 380,000 years old, showing slight fluctuations in temperature that correspond to the seeds of future galaxies and clusters of galaxies. After recombination, the universe entered a period known as the Dark Ages. During this time, there were no stars or galaxies, only vast clouds of hydrogen and helium atoms floating in the dark. Gravity slowly began to pull these atoms together, forming denser regions that would eventually become the seeds of stars and galaxies. During the Dark Ages, the universe continued to expand and cool. The density fluctuations observed in the CMB began to grow under the influence of gravity. These fluctuations were crucial for the formation of large-scale structures in the universe. An important but invisible player in this story is dark matter. Dark matter doesn't emit, absorb or reflect light, making it invisible to our eyes and instruments. However, it exerts a gravitational pull, influencing the formation of structures in the universe. Dark matter helped gather the gas clouds together, accelerating the formation of the first stars and galaxies. Dark matter is thought to make up about 27% of the universe's mass-energy content. Although we can't see it directly, we can infer its presence through its gravitational effects on visible matter, such as the rotation curves of galaxies and the motion of galaxy clusters. With the universe cooling further, it allowed these hot, energetic particles to combine more efficiently. The formation of hydrogen and helium nuclei was a crucial step, representing the universe's transition from a hot, dense state to a more structured and orderly one. This process set the stage for the next phase of cosmic evolution. As these gas clouds continued to collapse under gravity, they began to form protostars. The collapse increased the pressure and temperature in the core of these protostars until nuclear fusion ignited, marking the birth of the first stars. These first stars, known as population 3 stars, were massive and short-lived. They were composed almost entirely of hydrogen and helium, as heavier elements had not yet been formed. The intense radiation from these stars rayonized the surrounding gas, ending the Dark Ages and beginning the era of rayonization. The radiation from the first stars ionized the surrounding hydrogen, creating ionized bubbles in the intergalactic medium. As more stars formed, these bubbles grew and merged, eventually rayonizing the entire universe. This process took hundreds of millions of years, marking the end of the Dark Ages. With the end of the Dark Ages, the universe entered a new era. The first galaxies began to form from the gravitational collapse of dark matter halos, drawing in gas and forming stars. These early galaxies were small and irregular, but over time they merged and evolved into the diverse array of galaxies we see today. Clusters of galaxies are themselves grouped into even larger structures known as superclusters. Our Milky Way galaxy is part of the local group, which in turn is part of the Virgo supercluster. These superclusters form a vast web-like structure known as the cosmic web, with filaments of galaxies and clusters separated by enormous voids. With the formation of neutral atoms, the universe underwent a dramatic change. Previously, the dense, hot plasma scattered light in all directions, making it opaque. The recombination allowed photons to travel unimpeded for the first time, marking the universe's transition from an opaque fog to a transparent expanse. As stars and galaxies formed, they began to influence their surroundings through processes known as cosmic feedback. Supernova explosions, stellar winds, and active galactic nuclei, AGN, can inject energy and matter back into the intergalactic medium, affecting the formation of subsequent generations of stars and galaxies. Supernovae, the explosive deaths of massive stars, play a crucial role in enriching the interstellar medium with heavy elements. These elements, such as carbon, oxygen, and iron, are essential for the formation of planets and life as we know it. The universe has continued to evolve over billions of years, with galaxies merging and interacting, forming new stars and planetary systems. The study of this cosmic evolution, from the Big Bang to the present day, helps us understand the fundamental processes that shape the universe. The end of the Dark Ages. As the universe emerged from the Dark Ages, regions of higher density began to collapse under gravity. These dense regions, rich in hydrogen and helium, were the birthplaces of the first stars. This marked the end of the Dark Ages and the beginning of the reionization era. The universe had been dark and cold for millions of years since the formation of the first atoms. Gravity pulled together the diffuse clouds of hydrogen and helium gas, creating regions of higher density. These regions, called molecular clouds, were the nurseries for the first stars. As the gas collapsed, it began to heat up, eventually forming dense cores that would ignite into stars. Within these collapsing gas clouds, regions of even higher density formed, creating protostars. As the gas cloud continued to collapse, the temperature and pressure at the core of these protostars increased until nuclear fusion ignited, giving birth to the first stars, known as population 3 stars. The formation of protostars was a complex process. As the gas cloud collapsed, it fragmented into smaller clumps. Each clump continued to collapse under its own gravity, forming a dense core surrounded by a rotating disk of gas and dust. This disk played a crucial role in the formation of the star, as material from the disk accreted onto the core, increasing its mass. The growing protostar began to heat up due to the release of gravitational energy, eventually reaching temperatures high enough for nuclear fusion to begin. The ignition of nuclear fusion was a critical moment. In the core of these protostars, hydrogen nuclei fused to form helium, releasing enormous amounts of energy. This energy created an outward pressure that balanced the inward pull of gravity, stabilizing the star and allowing it to shine brightly. The process of nuclear fusion transformed the protostar into a main sequence star. The energy released by fusion reactions in the core created an outward pressure that counteracted the force of gravity, preventing the star from collapsing further. This delicate balance, known as hydrostatic equilibrium, allowed the star to maintain a stable size and temperature. The fusion of hydrogen into helium produced light and heat, which radiated from the star's surface, making it visible across vast distances. The large masses of population 3 stars meant they had very high core temperatures, which allowed them to burn their nuclear fuel rapidly. This made them incredibly bright and hot, emitting large amounts of ultraviolet radiation. However, their rapid fuel consumption also meant they had very short lifespans, typically only a few million years. The lack of heavier elements in these stars affected their structure and evolution, as elements like carbon, oxygen, and nitrogen play crucial roles in the fusion processes of more modern stars. As population 3 stars exhausted their hydrogen fuel, they began to fuse helium into heavier elements like carbon and oxygen. This process continued until the core of the star was composed of iron, which cannot be fused to produce energy. Without the outward pressure from fusion reactions, the core collapsed under gravity, triggering a supernova explosion. The energy released in the explosion was immense, outshining entire galaxies and sending shockwaves through the surrounding gas. The supernovae of population 3 stars played a crucial role in enriching the interstellar medium with heavy elements, paving the way for the next generation of stars and planets. The supernovae of population 3 stars played a crucial role in enriching the interstellar medium with heavy elements. These elements, such as carbon, oxygen, and iron, are essential for the formation of planets and life as we know it. This process, known as nucleosynthesis, set the stage for the next generation of stars and galaxies. The heavy elements produced in supernova explosions were scattered into the surrounding gas, mixing with the hydrogen and helium left over from the Big Bang. This enriched gas formed new molecular clouds, which in turn collapsed to form the next generation of stars. These new stars, known as population 2 stars, contained higher amounts of heavy elements, which influenced their structure and evolution. The presence of heavy elements allowed for more complex fusion reactions, leading to the production of even heavier elements over time. The continuous cycle of star formation, fusion, and supernova explosions gradually enriched the universe with the elements necessary for life. With the enrichment of the interstellar medium, a new generation of stars, known as population 2 stars, began to form. These stars contained higher amounts of heavy elements, making them cooler and longer-lived than population 3 stars. Population 2 stars began to form within the first galaxies. The formation of population 2 stars marked a significant step in the evolution of the universe. These stars had lower masses and longer lifespans than their population 3 predecessors, allowing them to live for billions of years. The presence of heavy elements in population 2 stars influenced their fusion processes, enabling the production of even heavier elements like silicon, sulfur, and iron. The formation of these elements contributed to the further enrichment of the interstellar medium, creating a fertile environment for the formation of planets and eventually life. As stars formed, they began to cluster together under the influence of gravity, creating the first galaxies. These early galaxies were small and irregular, but they played a crucial role in the evolution of the universe. Over time, these galaxies merged and grew, forming the larger and more complex structures we see today. The formation of galaxies was a complex and dynamic process. As stars formed within molecular clouds, their combined gravitational pull attracted more gas and stars, leading to the formation of dense stellar clusters. These clusters continued to merge and interact, eventually forming the first protogalaxies. Over time, these protogalaxies merged to form larger, more organized structures. The interactions between galaxies, such as tidal forces and mergers, played a crucial role in shaping their morphology and triggering bursts of star formation. The early galaxies formed a variety of structures, including spiral and elliptical galaxies. Spiral galaxies, like our Milky Way, have distinct spiral arms filled with young, bright stars. Elliptical galaxies, on the other hand, are more spherical and contain older, redder stars. These different structures are the result of various formation and evolutionary processes. The formation of spiral galaxies is thought to be driven by the rotation of the protogalactic cloud and the distribution of angular momentum. As the cloud collapsed, it began to spin, flattening into a disc-like structure. Density waves within the disk created the characteristic spiral arms where new stars formed. Elliptical galaxies, on the other hand, are believed to form through the merging of smaller galaxies. The violent interactions during these mergers disrupted the ordered motion of stars, resulting in a more spherical shape. Dark matter continued to play a crucial role in the formation and evolution of galaxies. The gravitational pull of dark matter halos helped gather gas and stars, stabilizing and shaping galaxies. Without dark matter, galaxies as we know them would not exist. Dark matter halos provided the scaffolding for galaxy formation. As gas cooled and condensed within these halos, it formed stars and galaxies. The presence of dark matter also influenced the dynamics of galaxies, affecting their rotation curves and overall stability. Observations of galaxy rotation curves have shown that the outer regions of galaxies rotate faster than can be accounted for by visible matter alone, providing strong evidence for the presence of dark matter. As galaxies formed, they began to cluster together under the influence of gravity, creating galactic clusters. These clusters are the largest gravitationally bound structures in the universe. Within these clusters, galaxies interact, merge, and evolve, leading to the diverse array of cosmic structures we see today. Galactic clusters are composed of hundreds to thousands of galaxies, bound together by their mutual gravitational attraction. The interactions between galaxies within clusters can trigger bursts of star formation, alter the morphology of galaxies, and drive the evolution of the cluster as a whole. The intracluster medium, composed of hot gas, fills the space between galaxies and emits X-rays, providing valuable information about the mass and distribution of dark matter within the cluster. The formation of stars and galaxies marked a new era in the evolution of the universe. Over billions of years, galaxies have continued to evolve through mergers and interactions, forming new stars and planetary systems. The study of this cosmic evolution helps us understand the fundamental processes that shape the universe. Today, astronomers use powerful telescopes and sophisticated simulations to study the universe's history and evolution. Observations of distant galaxies and the CMB provide crucial insights into the early universe, while simulations help us understand the complex interactions that drive cosmic evolution. The continuous cycle of star formation, supernova explosions, and galaxy interactions has shaped the universe into the rich and diverse cosmos we observe today. The life cycles of stars from birth to death. Stars are born in vast clouds of gas and dust known as stellar nurseries or molecular clouds. These regions are rich in hydrogen and other elements, providing the raw materials needed for star formation. The process begins when a molecular cloud collapses under its own gravity, fragmenting into smaller clumps. As these clumps collapse, they heat up, forming dense cores called protostars. The collapse continues, and the temperature and pressure at the core of the protostar increase until nuclear fusion ignites, giving birth to a new star. This process can take millions of years, and the result is a main sequence star, a stable star that fuses hydrogen into helium in its core. Main sequence stars are the most common type of stars in the universe, and they spend the majority of their lives in this stable phase. The energy produced by nuclear fusion in the core creates an outward pressure that balances the inward pull of gravity, maintaining the star's stability. The lifespan of a main sequence star depends on its mass. Small, low-mass stars, such as red dwarfs, can burn their hydrogen fuel for tens of billions of years. In contrast, massive stars such as blue giants burn through their fuel much more quickly, living for only a few million years. Our Sun, a medium-sized star, has a main sequence lifespan of about 10 billion years. The Hertzsprung-Russell HR diagram is a key tool for understanding the life cycles of stars. This diagram plots stars according to their luminosity and surface temperature, revealing distinct patterns that correspond to different stages of stellar evolution. Main sequence stars form a diagonal band on the HR diagram, with hot, luminous stars at the upper left and cool, dim stars at the lower right. As stars evolve, they move off the main sequence, following distinct paths depending on their mass. The HR diagram provides a visual representation of these evolutionary tracks, helping astronomers understand the processes that govern stellar evolution. As a star exhausts its hydrogen fuel, it leaves the main sequence and begins to evolve. For medium and low-mass stars, this involves expanding into a red giant. In this phase, the core contracts and heats up, while the outer layers expand and cool, giving the star a reddish appearance. In red giants, helium fusion begins in the core, producing carbon and oxygen. The energy from these fusion reactions causes the star to expand further, becoming a luminous red giant or, for more massive stars, a supergiant. These phases are relatively short-lived, lasting only a few 100 million years. In low and medium-mass stars, the onset of helium fusion can be sudden and dramatic, resulting in a helium flash. This event occurs when the core temperature and pressure become high enough to ignite helium fusion explosively, releasing a tremendous amount of energy. After the helium flash, the star settles into a stable phase on the horizontal branch of the HR diagram, where it continues to fuse helium into carbon and oxygen in its core. This phase can last for several million years, during which the star maintains a relatively stable size and luminosity. For stars with initial masses up to about 8 times that of the Sun, the end of the red giant phase leads to the formation of a planetary nebula. As the star exhausts its helium fuel, the outer layers are ejected into space, creating a beautiful glowing shell of gas and dust. The core that remains after the ejection of the outer layers becomes a white dwarf, a dense, Earth-sized remnant composed mostly of carbon and oxygen. White dwarfs no longer undergo fusion reactions, but they continue to radiate heat and light for billions of years as they gradually cool and fade. For massive stars, the end of the supergiant phase leads to a more dramatic fate, a supernova explosion. As the core contracts and heats up, it begins to fuse heavier elements, producing layers of increasingly dense and heavy elements. When the core is composed primarily of iron, fusion can no longer produce energy. The core collapses suddenly, triggering a supernova explosion that outshines entire galaxies and releases an enormous amount of energy. The outer layers of the star are blasted into space, enriching the interstellar medium with heavy elements. For massive stars, the end of the supergiant phase leads to a more dramatic fate, a supernova explosion. As the core contracts and heats up, it begins to fuse heavier elements, producing layers of increasingly dense and heavy elements. When the core is composed primarily of iron, fusion can no longer produce energy. The core collapses suddenly, triggering a supernova explosion that outshines entire galaxies and releases an enormous amount of energy. The outer layers of the star are blasted into space, enriching the interstellar medium with heavy elements. The core that remains after a supernova can become a neutron star, an incredibly dense remnant composed mostly of neutrons. Neutron stars are only about 20 kilometers in diameter, but can have masses up to twice that of the Sun. They possess extremely strong magnetic fields and can rotate rapidly, emitting beams of radiation that we observe as pulsars. In the most massive stars, the core collapse following a supernova can result in the formation of a black hole. Black holes are regions of space-time where gravity is so strong that not even light can escape. They are characterized by an event horizon, the boundary beyond which nothing can return. The formation of a black hole is a dramatic end to a star's life, but it is also a critical part of the cosmic cycle. Black holes can influence their surroundings, accreting gas and dust, and emitting powerful jets of radiation. They play a key role in the dynamics of galaxies and the evolution of the universe. Many stars exist in binary or multiple star systems, where 2 or more stars orbit a common center of mass. The evolution of stars in binary systems can be more complex than that of isolated stars, as interactions between the stars can influence their life cycles. In some cases, material can be transferred from one star to another, altering their masses and evolutionary paths. For example, in a close binary system, a red giant can transfer material to its companion, leading to the formation of an accretion disk and potentially triggering a nova or supernova explosion. Binary interactions can also lead to the formation of exotic objects like X-ray binaries and millisecond pulsars. Star clusters are groups of stars that form together from the same molecular cloud and are gravitationally bound. There are 2 main types of star clusters: open clusters and globular clusters. Studying star clusters provides valuable insights into stellar evolution, as the stars within a cluster are all at the same distance from us and share the same age and initial chemical composition. Open clusters contain hundreds to thousands of young stars and are found primarily in the spiral arms of galaxies. Globular clusters, on the other hand, are much older and contain hundreds of thousands to millions of stars. By studying the stars in these clusters, astronomers can test models of stellar evolution and understand how stars of different masses evolve over time. The life cycles of stars play a crucial role in the chemical evolution of galaxies, As stars form, evolve, and die, they produce and disperse heavy elements into the interstellar medium. This process, known as chemical enrichment, leads to the gradual increase in the abundance of heavy elements in subsequent generations of stars. Astronomers categorize stars into different populations based on their chemical composition and age. Population 1 stars, like the Sun, are rich in heavy elements and are found primarily in the spiral arms of galaxies. Population 2 stars are older and have lower heavy element abundances, while population 3 stars, the first stars to form in the universe, contained virtually no heavy elements. By studying the chemical composition of stars and galaxies, astronomers can trace the history of star formation and chemical enrichment in the universe. The life cycles of stars are an ongoing process that continues to shape the universe. As stars die, they enrich the interstellar medium with heavy elements, providing the raw materials for the next generation of stars and planets. This continuous cycle of star formation and death drives the evolution of galaxies and the cosmos as a whole. In addition to producing heavy elements, the deaths of stars can trigger new star formation. The shock waves from supernova explosions can compress nearby gas clouds, initiating the collapse that leads to the formation of new stars. This feedback mechanism ensures that the cycle of star formation and death continues, contributing to the dynamic and ever-changing nature of the universe. The life cycles of stars, from their birth in stellar nurseries to their spectacular deaths, are fundamental to our understanding of the universe. These processes not only create the elements that make up our world, but also drive the evolution of galaxies and the cosmos as a whole. In our next episode, we will explore the formation and evolution of planetary systems and how the elements produced by stars come together to create the diverse worlds we see today. The formation and evolution of planetary systems, from dust to diverse worlds. This migration can have significant effects on the architecture of planetary systems. For example, it can lead to the formation of hot Jupiters, gas giant planets that orbit very close to their host stars. It can also result in the scattering of smaller bodies, shaping the distribution of planets and debris within the system. As the young star matures and its radiation increases, the protoplanetary disk begins to dissipate. Stellar winds and radiation pressure drive away the remaining gas and dust, leaving behind a system of planets, moons, asteroids, and comets. This process, known as disk clearing, marks the end of the planet formation phase and the beginning of the evolutionary phase for the planetary system. The clearing of the disk can take several million years, during which the remaining material can continue to accrete onto planets or form smaller bodies. The final architecture of the planetary system is shaped during this period, with the orbits of planets and other objects stabilizing over time. The formation of gas giants like Jupiter and Saturn and ice giants like Uranus and Neptune occurs in the outer regions of the protoplanetary disk. These planets form through a process known as core accretion, in which a solid core forms first and then accretes a massive envelope of gas and ice. In the case of gas giants, the solid core grows rapidly, reaching a critical mass that allows it to capture large amounts of hydrogen and helium from the disk. For ice giants, the process is similar, but they accrete more ices, such as water, ammonia and methane, and less hydrogen and helium. The formation of these giant planets plays a crucial role in shaping the architecture of the planetary system, influencing the orbits of smaller planets and debris. Closer to the star, where the disk is warmer, terrestrial planets like Earth, Mars, Venus and Mercury form from the accretion of planetesimals and protoplanets composed mainly of rock and metal. These planets undergo significant heating and differentiation, leading to the formation of a dense core, a silicate mantle, and a thin crust. The process of accretion can be violent, with frequent collisions and impacts that shape the final size and structure of the terrestrial planets. During the late stages of formation, the planets may also capture or be impacted by large moons, as seen in the case of Earth's moon, which is thought to have formed from a giant impact. Moons and planetary rings are common features of planetary systems, formed through a variety of processes. Some moons are thought to have formed from the same material as their parent planets, accreting from the protoplanetary disk. Others may have been captured by the planet's gravity or formed from the debris of giant impacts. Planetary rings, like those of Saturn, are composed of countless small particles of ice and rock. They can form from the remnants of moons that were torn apart by tidal forces or from the debris of collisions and impacts. The study of moons and rings provides valuable insights into the history and dynamics of planetary systems. Comets and asteroids are remnants of the early solar system, providing valuable clues about its formation and evolution. Comets are icy bodies that originate from the outer regions of the solar system, such as the Kuiper belt and the Oort cloud. When they approach the Sun, their ices vaporize, creating a glowing coma and tail. Asteroids, on the other hand, are rocky bodies that primarily reside in the asteroid belt between Mars and Jupiter. They are thought to be the remnants of planetesimals that never coalesced into a planet. Both comets and asteroids have played significant roles in shaping the planets through impacts and may have delivered water and organic molecules to early Earth, contributing to the emergence of life. The discovery of exoplanets, planets orbiting stars outside our solar system, has revealed a remarkable diversity of planetary systems. These systems come in a wide range of sizes, compositions, and architectures, challenging our understanding of planet formation and evolution. Some exoplanets are similar to the planets in our solar system, while others are unlike anything we have seen before. For example, super-Earths are planets with masses between that of Earth and Neptune, while hot Jupiters are gas giants that orbit very close to their host stars. The study of exoplanets provides valuable insights into the processes that shape planetary systems and the potential for habitable worlds beyond our own. The search for habitable planets, worlds that could support life, is a major focus of modern astronomy. The concept of the habitable zone, the region around a star where conditions are just right for liquid water to exist, is central to this search. However, habitability depends on many factors, including a planet's atmosphere, magnetic field, geological activity, and the presence of essential elements like carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. The discovery of potentially habitable exoplanets, such as those in the TRAPPIST-1 system, has sparked excitement and interest in the possibility of finding life beyond Earth. The study of these planets and their environments is a key area of research, as scientists seek to understand the conditions that make a planet habitable and the likelihood of life elsewhere in the universe. Future missions, such as the James Webb Space Telescope and the planned missions to the outer planets and their moons, promise to revolutionize our understanding of planetary systems. These missions aim to study the formation and evolution of planets, search for signs of life, and explore the diverse environments of our solar system and beyond. The formation and evolution of planetary systems, from the birth of planets in protoplanetary disks to the diverse worlds that populate the cosmos, are fundamental to our understanding of the universe. These processes not only create the planets and moons we see today, but also set the stage for the potential emergence of life. Understanding the conditions necessary for life is the first step in the search for extraterrestrial organisms. Life as we know it requires liquid water, a source of energy, and the right chemical ingredients, including carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. The concept of the habitable zone, or the Goldilocks zone, is crucial in this search. This is the region around a star where conditions are just right for liquid water to exist. However, recent discoveries have shown that life might exist in more diverse environments than previously thought, such as beneath the icy crusts of moons like Europa and Enceladus. The search for life in our solar system focuses on several key locations. Mars, with its past presence of liquid water and current subsurface ice, is a primary target. Missions like NASA's Perseverance rover are exploring the Martian surface, searching for signs of past microbial life. Europa, one of Jupiter's moons, is another intriguing target. Beneath its icy surface lies a subsurface ocean that may harbor life. Future missions, such as NASA's Europa Clipper, aim to study this ocean and its potential for habitability. Similarly, Saturn's moon Enceladus has geysers that spew water vapor and organic molecules, suggesting a subsurface ocean that could support life. The study of extremophiles, organisms that thrive in extreme environments on Earth, provides valuable insights into the potential for life elsewhere. Extremophiles live in conditions that were once thought to be inhospitable, such as deep-sea hydrothermal vents, acidic hot springs, and the icy depths of Antarctica. These organisms demonstrate the incredible resilience of life and expand our understanding of the possible environments where life could exist. By studying extremophiles, scientists can develop models for the types of life that might be found on other planets and moons. The discovery of exoplanets, planets orbiting stars outside our solar system, has revolutionized the search for extraterrestrial life. Missions like NASA's Kepler and TESS have identified thousands of exoplanets, many of which are in the habitable zones of their parent stars. Astronomers use a variety of methods to detect exoplanets, including the transit method, which measures the dimming of a star's light as a planet passes in front of it, and the radial velocity method, which detects the gravitational wobble of a star caused by an orbiting planet. These methods provide information about the size, mass, and orbital characteristics of exoplanets. One of the most exciting developments in the search for extraterrestrial life is the ability to characterize the atmospheres of exoplanets. By studying the light that passes through or is reflected by an exoplanet's atmosphere, scientists can identify the chemical composition and potential signs of life. Spectroscopy is a key tool in this endeavor, allowing astronomers to detect molecules such as water vapor, methane, carbon dioxide, and oxygen. The presence of these molecules, especially in certain combinations, could indicate biological activity. Future telescopes, such as the James Webb Space Telescope, will enhance our ability to study exoplanet atmospheres in detail. Biosignatures are indicators of life that can be detected remotely. They include specific molecules, such as oxygen and methane, that are associated with biological processes. The search for biosignatures involves identifying these molecules in the atmospheres of exoplanets and understanding the geological and biological processes that produce them. For example, the simultaneous presence of oxygen and methane in an exoplanet's atmosphere could be a strong indicator of life, as these gases would react with each other and need to be constantly replenished by biological processes. The detection of biosignatures would provide compelling evidence for the existence of life beyond Earth. The SETI, Search for Extraterrestrial Intelligence program, is a major effort in this field, using radio telescopes to listen for signals from other civilizations. While no definitive technosignatures have been detected so far, the search continues, and advances in technology and data analysis are improving our ability to detect potential signals. The Fermi paradox addresses the apparent contradiction between the high probability of extraterrestrial civilizations existing in the universe and the lack of evidence for or contact with such civilizations. Named after physicist Enrico Fermi, the paradox raises profound questions about the nature of life and the universe. There are many potential solutions to the Fermi paradox, ranging from the idea that intelligent civilizations are rare or short-lived, to the possibility that they are avoiding contact with us. Other theories suggest that advanced civilizations might be using communication methods that we cannot yet detect or understand. The Drake equation is a formula used to estimate the number of active, communicative extraterrestrial civilizations in the Milky Way galaxy. Developed by astronomer Frank Drake, the equation takes into account factors such as the rate of star formation, the fraction of stars with planets, the number of habitable planets per star, and the likelihood of life, intelligence, and technological civilizations developing. While the Drake equation involves many uncertainties, it provides a framework for thinking about the factors that influence the likelihood of finding extraterrestrial life. By refining our estimates for each term in the equation, we can improve our understanding of the potential for life in the universe. Astrobiology is the interdisciplinary study of life in the universe, combining fields such as astronomy, biology, chemistry, and geology. Astrobiologists seek to understand the origin, evolution, distribution, and future of life on Earth and beyond. Research in astrobiology includes the study of extremophiles, the search for biosignatures and technosignatures, the exploration of habitable environments in our solar system, and the study of planetary formation and evolution. Astrobiology provides a comprehensive approach to the search for extraterrestrial life, integrating knowledge from multiple scientific disciplines. The potential discovery of extraterrestrial life raises important ethical and philosophical questions. How would we respond to the discovery of microbial life on another planet or the detection of an intelligent civilization? What are the implications for our understanding of life and our place in the universe? The search for extraterrestrial life is an ongoing and evolving endeavor, driven by advances in technology, new discoveries, and our innate curiosity about the universe. Future missions and telescopes, such as the James Webb Space Telescope, the European Space Agency's Plato mission, and the proposed LUVOIR, Large UV Optical IR Surveyor Telescope, promise to enhance our ability to detect and study potential signs of life beyond Earth. As we continue to explore our solar system and search for exoplanets, the possibility of discovering extraterrestrial life remains one of the most exciting and profound questions in science. The search for life beyond Earth not only advances our understanding of the universe, but also deepens our appreciation for the uniqueness and diversity of life on our own planet. Stay tuned and subscribe to Let's Learn How the World Works to continue this cosmic journey. Understanding the potential for life beyond Earth not only satisfies our curiosity, but also provides insight into the fundamental nature of life and the universe. Thank you for joining us, and we'll see you in future episodes as we continue to explore the wonders of the cosmos.